Hello? Okay. Good morning, everybody. So this is a small crowd compared to what I'm used to, but it's been a long time since I've spoken public. So I came up, Entric wanted me to speak here, and I had a problem coming up with talk titles. So these talk titles are kind of weird, but we made them up together. And Talk 2's title actually fits better for today, because the chip I'm about to talk about is a Samsung IC for the printers. And this IC is worth millions a month. These printer companies like Apex, I believe they're out of Korea, they're making millions on the Samsung printer line, on the laser toners, aftermarket toners. And Samsung's doing whatever they can, HP's doing whatever they can. They're all incorporating Smartcard ICs today to protect their toner or their ink. Even their ink. A $10 ST ink cartridge has a IC inside that would cost you several $100,000 to get it reverse engineered. So with that, let's start. If those who know me, I don't do PowerPoint really. So I want to take you into my world, which is Photoshop. I'm not at Oliver's level yet with an automated tool. So I just want to give you, for the next 45 minutes, like an overview of basically what's gone on in life. Let me zoom out here. Actually, hold on. We'll go to this in a second. So this IC had a shield, a secure, it was, I believe, 4 metal layers. This is not my laptop, by the way. This is Antric's laptop. And it's not working. Okay. It doesn't want to go. I'm touching it. Sorry, everybody. Yeah, that one. Okay. So can everybody see this okay? I can zoom it in larger if you need to. So this was a four metal layer device, 130 nanometer shrink, aluminum process, wasn't copper yet. And normally everything under 130 is going to be a copper process. This is all SEM image, scanning electron microscope. If you've heard the word before, or you might have one. And so this chip had been, this is the results of several devices. So several devices were taken, they were polished down, they were thrown into acid, fuming nitric or fuming sulfuric, and each one was polished to a different level. So the first one, strip the shield off, strip off this protective metal layer on the surface. All it is straight lines going across the chips. And honestly, it's a waste of time. It's an obstruction, but when you have a focused ion beam workstation, the shield does nothing. I broke every shield I've ever come across in minutes. So basically, right here we have our top metal under the shield. So we polish to this level. Then we take another chip. We get to this level. We compare the two chips. Okay, which one looks nicer to us? Okay, this one looks nicer. Keep it. Now let's go one layer lower. So we're going to polish it down. Every layer we're going to strip down on these chips. These chips are destroyed. You know, they're throwaways afterwards. And so you've got, we don't care about that shield again, that active shielding on the surface. You'll see some pictures of it in a little bit. So we've got our top metal, which is just wires. Then we've got metal 2, which is more routing, more wires. And then we have our logic layer, which wasn't green and red. I painted that. That's my VDD and ground rails. Just for a quick, when I'm looking at a gate, and I want to figure out what a gate does, I've got to look at metal 1 and poly. So the actual transistor layout, the dopings, for the wells, for the different, P-type or N-type dopings. So this is what got done to this chip. Then it was thrown into a SEM and it was imaged at, I believe, 20,000 times. So zoomed in 20,000, optical microscope can go up to about 1,500, and this is 20,000. And SEM can go up to 1 million in zoom. So even if this was a 10 nanometer process, it's going to be very hard to polish. This device was polished down using a combination of techniques called reactive ion plasma etching, as well as manual polishing. So the Rye etcher does a good job, but sometimes you have little pockets in the oxide. If there's gaps where if there's a space like here, like right here, you might get a gap. You might see a dip in the result. So then you throw it on the polisher, you can clean this up and get the results you see here. The whole time I'm talking, if anybody has a question, just throw your hand up. This is very informal today. I just want to take you into my world and see what happens. I'm the only one doing this stuff. I don't have a team of people. It's all me. So I've got to do the acid. I've got to do the polishing. I've got to do the imaging, the stitching. I've got to get them aligned, the layers aligned, because every one of these layers is perfectly aligned in the Photoshop picture. Something that Oliver knows is not easy to do all the time. Yes, sir. What kind
of manual polishing?
I use an Ultratech Ultra Pole.
Is it 5-axis?
I'm sorry?
Is it 5-axis?
I don't I don't understand.
When you're polishing the die, does it like use 5-axis?
No. It's just a disc. They're about $13,000, and it's just a disc. It's a heavy piece of equipment that's it's about this big and that long, that high, and it's got a disc on top with with a felt pad. And I use my finger with the chip when I'm done. So it goes through a Rietch process first, reactive ion plasma etcher, and then after that. After we get down, we remove the oxide. Next, we run a process to remove the metal. Then I'll look at it. I'll throw a real quick with my finger on the polisher. So I've got videos. I had videos before, and people have heard this from me before. So I'm trying to get right into the SEM picture itself and not focus on the techniques so much. So we've got this chip. It's 130 nanometers, which I have to say is pretty small. Stuff has gotten smaller. Like here's before we get specifically into Samsung, it doesn't work. This is a new Mac. I'm on a 2011 Mac, so thank goodness the Photoshop is open. So here, this is a 90 nanometer ST. Oliver's lab back in France helped me do this one, actually. If you remember, maybe this is an ST23. This is used also in a printer cartridge. And so these guys are hiding behind these common off-the-shelf smart card ICs. And this is something I'll talk about at the end of the talk today. They're putting millions. They're trying to save millions of money a year in revenue, but they're not doing anything custom inside this IC. If they had customized this IC, they would have thwarted a lot of attackers possible. So you can see even at 90 nanometers, the only thing that's different to me is the way the logic looks on poly, and a little bit of metal one too. But it takes you 5 minutes to get used to this. So even as they shrink smaller and smaller, it just means you're zoomed in more and more with your SEM. So we've got this chip. I'll zoom out. I cropped this picture. This picture is 7 gigabytes. And the other picture I'm going to open is 14 gigabytes, which is nothing. I have a picture at my office that's 150 gigabytes. And it's a combination of SEM. I had a Chinese lab do this for me rather than me do it myself. And the Chinese lab gave me back 10 gig layers, each layer. So each of those layers I showed you guys was 10 gig per layer. And then once they got into Photoshop and Photoshop converts them into their formats, turned out to be a 140 gigabyte picture. I had to stick 512 gig of RAM into the computer with a dual Xeon processor. So I've got this monster to do all this work on. But now I'm on Entrix MacBook Pro. Yeah. So this chip is a weird chip. It's a secure COM from Samsung. I don't have a data sheet on it. Didn't really need one. I was able to find data sheets from other processors that Samsung makes that gave me enough insight into the instruction set and so forth, what to expect on boot up. It had a very small ROM. Can you guys see this? It's pretty dark. Can everybody see the pictures? Is there some way to brighten this on the projector? Okay, so this is part of the ROM. I cropped it here. So this was I believe a 24 kiloword by 16-bit output. So you had a 16-bit half here, 16-bit half here. You had an EEPROM over here. That's out of view as well because I cropped it for size. The EEPROM wasn't code executable. So this chip only runs code from its ROM. So the EEPROM is only holding secrets. And this is exactly what everybody's after for the printer. They want the secrets. This chip's got a bunch of symmetric cryptographic algorithms inside, as well as asymmetric crypto. So there's an asymmetric wrapper, and that's the one thing nobody can get except Apex in China and a company called Static Control out of North Carolina, I believe. They have the key. How they got the key, I have no clue, because it's locked up pretty deep inside here, and it's not in the printer. You can get one half of the key out of the printer, but the other key is sitting inside this chip. But Samsung sued some Koreans back in like 2011, claiming that someone inside sold secrets. So who knows what happened. But the key is known. These guys are making over $1 million a month. So to attack this chip, there was nothing else special about the chip. It had a bunch of static RAM. You can see here's a block here. So wow, I'm sorry, it's because it's SEM. Tomorrow's pictures are going to be all optical, so you'll be able to see beautiful colors and everything. It'll be very bright on the screen. This is the problem with the SEM. The SEM is black and white, shades of gray, so to speak. There was a static RAM here. So the chip has a bunch of RAM inside, and it's got a small ROM. So if you wanted to attack this chip, the first thing you're going to do, you have to think to yourself, well, how does it function? Well, it powers up. This super secure chip powers up from its ROM. It's where every chip powers up from. They boot from their ROM, or if they don't have a ROM, they'll boot from their flash. It depends on who makes the device. So the first thing that I started to do was to trace their ROM. So you can see here, like I've got each line highlighted in a different color. So, 0 to 15. Now these are out of order. The ROM is heavily encrypted. Not heavily encrypted, but it goes through a process of some XNORs. For some reason, they decided to use XNOR gates, not XOR gates, to decrypt their fetch. And they played around with their crypto on where you've been last to help decrypt the value. So this ROM is done kind of old school. You can see it exits out here, and then they literally wire tied the left side of the ROM to the right side of the ROM. So they didn't output 32 bits into logic and then deduce, okay, which side do I want, the even or the odd side? They basically said, we're going to tie these wires all together. So the left side and the right side, bit 15, are physically together on a wire, and then we're going to control their output enable lines. So it's a different way of doing business. I wouldn't have done it like that, but that's what they've chosen to do. So if you follow this, and the first thing you can see here is where I started to look. I started to look for fib access. When you're working with this chip, it has the shield on the surface, which is, as I said, straight lines going across. And give me 1 second. Okay, I'm making sure all the layers are on. Yeah, so you can see here, there's a VDD rail right here, and there's a ground rail right here. And this is the perfect access point to hit their bus. But the problem was, I didn't know their ROM was encrypted in the beginning. So I actually wasted time and put down 17 needles in this area. Hold on a second. So you can see all the different colors. And then all of a sudden, and the reason I thought I hit the jackpot so fast was because within the 10 minutes of looking at this image, not 10 minutes, but within a very short amount of time, I hit a bunch of flip-flops in this area right here. So when your data bus comes into a flip-flop, you're usually in the right spot. Usually. Excuse me. If we turn off. So now you can see I've got numbers. So there's a flip-flop sitting right here with the 3. So the flip-flop runs from about here to here. They're very large elements in logic. Flip-flops are very easy to spot. You can spot them in seconds. They're not even worth tracing out. You have a clock, an input, an output, and probably a set or a reset line. And that's it. So it comes into this block of logic, and I thought, jackpot, we hit it. But I did notice the data bus continue to go into the core deeper. But I was thinking, well, okay, there's flip-flop group here, and then the data bus is going to continue for the operand, jump or add what, add how much, this type of stuff. And so I put down needles, I did the edit, and the data was junk. It was just junk because it was encrypted still. So what this turned out to be, when then I'm looking at this and I'm going, something's wrong here. Let me trace deeper. I have allergies, I'm sorry. So I said, let me trace deeper. And what I realized was that these flip-flops are latching the cryptid value of their ROM output, and it feeds into a bunch of XOR gates. But there's only one output for this whole entire area. So there's a 17th flip-flop, which I don't know why it's there. It doesn't do anything. And can anybody think of what this did? It's actually pretty cool. And I don't know why it's here, and it doesn't do anything because I tampered with it. It's a parity generator. That's all this does. It's a bunch of XORs. They're running parity. I believe it was even parity. It doesn't. I don't care if it was odd or even. It doesn't make a difference to me, for my purposes. But they put not a tamper. They put a parity generator in circuit on the cryptid fetch of the ROM. Why? I don't know. It'd be described in the datasheet probably. Tampering with the one-wire output of that generator didn't do anything. It didn't shut the alarm down, or it didn't trigger any type of alarm to shut the chip down. Another thing I might say about this chip for being so secure, when I would cut the shield to make a circle, see if I can open a picture here. So you can see here, this is what it looks like in a focused ion beam workstation machine. So you can see, here's for reference. So I even cut an arrow into the oxide. That's an arrow. So I lost my train of thought. I'm sorry. So I put down 17 needles. You can see here, and then here's the set of a flip-flop. Why do I want to mess with the set? Because I can control the output of every one of those flip-flops with one needle. So with one needle, I can set that output to 0 or 1, which in most cases is 0 works perfect to walk through time. The whole goal here is to get the contents of the ROM out and then look at how you can manipulate the ROM code to get your EEPROM contents out. It's, for example, this chip speaks secure channel. So it's a secure channel from the printer from the moment it powers on. So the printer powers up, sends in a challenge, stuff like this is happening. They pass a key, encrypted, and nothing is in the clear. You can't see the serial number of the toner, nothing. Where 10 years ago, you could see the serial number of the toner in the clear. Everything was in the clear. So you can see in the fib, to get these circles, I moved over from a bond pad, so many microns over, so many microns down, and then I made windows right here. So using a gas called xenon difluoride, I was able to basically remove the oxide, because a chip is made out of metal and oxide, basically. And so right here, and these are basically windows, so I can see through these, like it looks like a jail, like a jail or something, which is the active shielding. Which didn't work, by the way. That was what I was going to say. I forgot. I'm a little nervous. Yeah. So the active shielding on this secure device didn't work. The parity generator on this secure device didn't even work. I'm not sure what they're up to, but I don't know. So I could make a hole in the shield like I did for all of these circles. So what these circles are, there's a hole through that shield. I removed the wire, physically removed the shield line, drilled down deeper, hit the wire I was after from the Photoshop picture, and then filled that hole with a via of platinum. I can use platinum or tungsten, and then I deposited a platinum circle, as you can see on like number 12, number 13, number 4. And then there were some weird things where the chip would sometimes die. So then I thought, okay, maybe there's a random check in the ROM, in the contents of the ROM that says, is the shield working? Has the shield been tampered with? This is most likely what the manual tells the software designer to do, is basically, read a register in memory, and the register is going to tell you or stuff a value into a register and read it back from another register. And if you get your value back, or whatever their little formula is, the shield is working. But at no time, the chip would just stop running. It wouldn't die. Yes?
Sorry, what is the shield made of?
Shield's made out of aluminum. Very thin wires of aluminum. I believe on the surface of this chip, the wire size was 200 nanometers, I think. 250 nanometers on top metal. The wires on the surface are larger than as you get lower. As you get to metal 1, the wires shrink down to, I believe, like 180 nanometer wire size. So they get thinner, smaller. Exactly. Yeah. So like here, the chip has no clue I made this hole. This hole was done with xenon difluoride gas. So I stick a needle into the chamber of the fib, and I draw a box, and I tell it mill. And then all of a sudden you'll see these wires right here, the whiteness here. It'll light up white like you can see in this picture. This is almost exactly like it looks like live on the machine. I mean, it's a screenshot that I took off my camera. And so now I keep milling, but xenon difluoride gas, it etches oxide 7 times faster than without the gas. With just the beam. If you just use the beam, you're pushing the material around. You're not really removing it cleanly. When you run the gas, even if you ran a tungsten or platinum gas at the wrong beam current to not deposit, it would keep the hole clean too. So, but ultimately you want to use the XEF4, xenon difluoride. And so xenon difluoride slows down the etching of metal, but enhances the etching rate of oxide, of glass. So here you can see in these windows to find where am I in the right spot? I'm looking for specific wires that I'm familiar with from the Photoshop picture. So I make these windows. The chip has no clue that I made these windows because the shield wires are still intact right here. They're perfectly fine. They're just exposed to the atmosphere. Do you follow me? So the chip has no clue. But again, like I said, I could make these circles, do these deposits. I'm going down to metal 2 in some cases. So in some cases, there's metal 4 was that shield, metal 3, metal 2, metal 1. Metal 1 is the logic, metal 2 and metal 3 were routing of the, wire routing. Just like on a PCB, routing. Some cases, the hole that I made before that circle got placed was 2 layers down into the chip. And I only started fixing, you can see here, I deposited platinum. So I broke the line. I cut this line. So now I took platinum and I went up, over, and down again to fix it. It's not quite as nice as my Infineon attack was on the TPM. The Infineon attack, I made bridgings. I'll talk about this tomorrow for 5-10 minutes. So this was quick and dirty. It did the job. Because their active shield was like 32 different circuits. So it was like 32 different wires doing something. But as I said, tampering with the shield the chip still ran. Talked no problem. Just sometimes I'd see these random chips stop talking. Fix the shield and they'd run again. You can see here too. Here again, I dug a window. I'm looking for a reference because I'm pretty far away. This is about 5 hours on a fib. Yes.
How do you create that bridge without shooting
I can't hear you, Adam.
How do you create the bridge without shorting the lines up?
Oh, you do what's called a cleanup. So you can see like here, this black right here is where after I did my deposits, here I goofed up here. So I goofed up when I was on the fib for number 4. So you can see I ended up cutting 2 lines for number 4 for some reason, and on this particular chip. So you can see here I went down, over, and up with the platinum deposition, and then again I went up, over, and down, put the circle, and then you can notice here there's black. Let me see if I can zoom this photo in. Yeah, well, I have to isolate. Otherwise, I create shorts. Everything white here is platinum spray. Oh, look, I even wrote numbers into the chip. This work is 2016, so this has been sitting in my hard drives for the last 3 years, and I'm still stuck in time. But I wrote numbers, and again, this is all platinum. Everything's platinum. Platinum's like $600 for 5 grams, 2 grams, something like that. And it'll last you for a few years. I've never replaced my platinum gas. I've only replaced my xenon difluoride. Xenon difluoride lasts me about 6 months on the machine because I use it all the time, every day almost. And it's about $2,000 to replace it, to exchange it. Much cheaper. So you can see, here's the circle. Here's the edit was right here. And then the circle's connected into that hole right there. The shield's been cut over here and cut over here. And then it's been jumpered here. jumpered there. And then this is all isolation right here, this black. So I went, because everything here, this is all platinum spray. So this is all overspray. It's just like a spray can. So when you're depositing a metal in a focused on beam workstation, you get a lot of overspray. And the end result is what you can see here. You can see it gets dark because that's absorbing the beam. So the black is oxide, and here's where I've sputtered down platinum. Not on purpose. Actually, it was on purpose. Yeah, because there's way too much spray. You can see I was just rolling around in the machine with the joystick, just spraying with the gas open. So you leave the valve open on the platinum, and you run a beam current that's going to drop it, that's going to deposit, and you just walk around, and it just lights up on the screen, because otherwise you're in pitch black. You're in total darkness. There's some challenges, with using a focused on beam workstation in the SEM. So anyway, that's a successful 17-hole drop. So then I came across a bunch of stuff on this chip. I made schematics on paper. This is nothing like Oliver's stuff. Oliver's automated the whole process. But you can see here, yeah. Yeah, to walk it with a single needle. So I walked it 16 times with 2 needles down. 1 needle messing with the set line of the whole entire group of flip-flops, and 1 needle on 0, then on 1, then on 2, then on 3, and so forth. The whole idea of the set line was to make it think the last instruction executed is still being executed, even though on the front side of the flip-flop you're getting 10, 20, 30, 40. On the output you're still getting add 10, add 20, or something that doesn't branch. So you can see the first thing that comes out, the ROM comes out right here, and it goes into what I call a buffer. It's just a buffer. It's a couple inverters in series, or in series to each other. And then it went to what I call flip-flop group 1. And flip-flop group 1 was the parity generator that I talked about. So this was the first place I went to, as I said, because I saw the flip-flops. I got all excited, got too excited, in fact, and wasted, like I said, it's a 5-hour edit to show you those 17 holes, which is shorter than Infineon. Infineon was a 6-hour edit. Then the bus keeps going down, and it hits an XNOR gate, what I called XN1. So this is first stage of decryption of the value, which is when I realized, okay, now I'm onto something. And it gets even better. I hope I'm not running out of time. I barely started. How much? 10 minutes is all I have left? Okay. I don't know what I'm going to do tomorrow. Tomorrow, the picture's much better. We're going to go over a bunch of different chips: Atmel, ST, Infineon, EM Micro. I'll have like 10 minutes on each one, and they're all optical. They're not going to be SEM like this. They're a little bit larger, but it's all principles. Atmel's been doing more with their crypto than any of these other chip companies, which is kind of strange, because Atmel's not really that good with their smart cards. So the B input, I didn't care, because when you're tracing through the logic, and I'll try to find these gates in the Photoshop for you guys, but when you're tracing through the logic, you see 2 inputs to an XNOR, XOR, and then you see 1 output. The output's the largest line you're going to see, and I'll show this on the pictures. So it's real easy to just say, okay, the data came in here, who cares what B was, let's keep going. Because what are we looking for? We're looking for a flip-flop. Because remember, you can't go into this flip-flop and then the output keep going with the bus, because what you just did was cut your frequency in half. A flip-flop divides by 2. So if you're at 20 megahertz, that flip-flop just knocked you down to 10. So this is why I'm saying, like, you run into a flip-flop, they got me with the parity generator, but you can tell if it's right or wrong if you spend enough time on it when you hit the flip-flop group. So it goes into XNOR 1, output comes into another buffer, it goes into another XNOR, second one. And then notice the B input was data bus bit 1. So the crypted D1 value, or I believe it was the crypted D1 value, fed into the B input. And I didn't really care. I just did something I came across, so I documented it. Then the output goes through an inverter to another inverter. The bus went to the right too, but it went to a bunch of AND or invert logic. If you guys have heard this, anybody who took Oliver's class probably heard these words. AND or invert. You make any gate out of AND or an invert. Yeah. So we didn't care about that. It goes through 2 inverters, which these are basically buffers. They're buffering. And then again, it goes through an inverter. And then you can notice here, I'm basically saying, put the fib needle down right here. Now, this is something I want to get into. This is really good. I like this. Notice I say there's flip-flop 1, flip-flop 2. And notice there's an inverter in front of flip-flop 2. Everybody see that? And then here's the direct output. So you could put your needle down here or here. You just have to note, okay, was I inverted or was I direct on what it was? So let's go back to that Photoshop. This Flipflop 2 gets... Oh, I got rid of it. Give me a second. I'm going to open a different picture. Flipflop 2 is very interesting. I'm calling it anti-fly logic. And there's a reason there. So they went through the... Okay, it's opening. They went through the liberty to put down, instead of... So this was their instruction register area right here. They took the liberty of adding a second flip-flop for all 16 bits. So you had... Every data bus bit had flip-flop 1 and flip-flop 2. All flip-flop 2 did was prevent me from tampering with flip-flop 1. If I tampered with flip-flop 1, they ran on different flip-flop clocks. So everybody in here probably understands a flip-flop takes a clock. So all of the data bus bits with flip-flop 1 use the same common clock and the same set line. But flip-flop 2 ran on a separate clock. It's the same clock, but it wasn't connected to the same signal. It was coming from a different driver. So the reason for this, Flipflop 2's only purpose in life was to prevent me from tampering with Flipflop 1. But Samsung made one big master mistake, which a lot of these RISC processors do. If you ever look at the instruction set of these RISC processors, I almost guarantee you that one of the high bits represents branching. So if I take a needle, and I'll show you this tomorrow about Atmel's AVR series on their smart cards. Same thing goes for calm RISC, secure RISC. If you take a needle, or if you take D15 and you cut it and you strap it to a 0 with the fib, or you put a needle down on D15 and you prevent D15 from toggling to a 1, the chip can't branch. If the chip can't branch, the chip powers up at 0 or wherever it powers up, and it goes to 1 to 2 to 3 to 4, like it thinks it's adding. So the instruction becomes something, but it's not a branch. So same thing happened with the Samsung chip. So let me find that area. And Trick, it's very difficult to use. No, I'm okay, but it's definitely a different MacBook than I'm used to. So I highlighted the flip-flops in different colors. Okay, there we go. So you can see 1414. And then you can see here, if you can read my writing, it says D8 XOR trap. Everybody knows an exclusive OR. 1 and 0 is 1, 0 and 1 is 1, 0, 0 is a 0, and 1 and 1 is a 0. So the output of that schematic that I showed you, so the output, these two had to be opposites. They're outputs. They're registered output, of the they're clocked output. So if 1 and 1, if it's not 1 and 0 or 0 and 1, an alarm went off. So they actually, let me see if I can find it. Samsung actually put in an alarm in case I tampered. You can see right here, 4 NAND. So this is a 4-input NAND gate. And anybody who's into logic, you can see, I'll show you the poly. You can see what the NAND gate looks like. You can spot it very quick. You can see here's your P channel, here's your N channel of your wells. You can see the P channel is always larger than the N channel. So it's very quick to see which rail is VDD and which rail is ground on a device, on a semiconductor. So the reason for this 4-input NAND was to handle all of these flip-flops, XORs. So the result of the XOR feeds into these NANDs. And then these NANDs went to, I believe, a NOR gate, a multiple input NOR gate. And so the truth table for a NAND is like all ones is a 0. If anybody goes to a 0, it's a 1 output. So if this thing fired off a 1, the chip shuts down. But why didn't they erase their secrets? ST Microelectronic out of France will erase their EEPROM, their double EEPROM or their flash on their devices if I tamper with their shield or if I do anything weird inside their chip. And Samsung just says, we're going to pause, we're going to freeze, we're going to lock up, we're not going to execute anything. So it's kind of strange. So by cutting the 15 line here on this chip, I was able to get the ROM contents. And then the whole goal was now I need to understand the ROM to get the double EEPROM out. And so the whole idea was, okay, see what they're doing with their math, with their cryptography, to send in a packet that requests the key that I'm after be read from its EEPROM. And then I sit with needles and I capture the key as it comes out of the chip. So that'd be about 3 needles. It'd be 1 needle to do the glitch, to basically, so it's sitting on the bus, sitting, 1 second. So sitting on the bus here, I can tamper with them momentarily, meaning as instruction code to branch comes down, I can turn it off if I put a needle on the 15 line. So I put a needle on D15, not D0, obviously. And at a certain clock cycle in time, I drive a 0 into the chip, or I drive a 1. And that's another problem with these chips. The only problems that I run into in life is getting them polished down as they get smaller. Because some of these chips are not even a half millimeter square. They're so tiny now. They're getting very small. But once it goes into the fib, it's done. I'm out of time. So the bottom line was Samsung got rid of this chip. These chips were costing me about $110 each to get. I went through about 15 of these chips, and then Samsung pulls a quickie on me, and they switched the chip they're using. So they went from this IC to an IC with the same exact techniques inside, just a different chip, different layout. But I did a quick look at it and just said I walked away from it. Yeah. Does anybody have questions?
Why did you walk away from it?
Frustration and money.
Would you say that was effective?
It was effective, but the Chinese have the key. They've got it. I was promised $250,000 a month if I cracked the key on this chip. It's a lot of money. I don't know how many people make even $250,000 a year. It's a lot of money. And this is something I see. These guys are flying around in helicopters and private jets, private planes. Printer industry is something it's legit. There's nothing wrong. You own the printer. Why do you have to buy a toner from Samsung or from HP? Why can't you buy an aftermarket toner? I prefer the original OEMs, but you never know.
What if we just, after a summer, trying to send you the chip? Would that work?
Yeah, it would. Yeah, if you have it still. This was a Samsung D101, 111, 116 toner. And today the chip's probably changed again. And to even to get these images, these are very nice SEM images. And to get an image of this quality, forget the coloring. The coloring, that's all me. These were black and white before you had them.
So that's a really good point. Why did you just crowdsource the chip?
Because I'm alone and I don't really know how. I would go buy these at Office Depot.
Just make a Patreon.
Yeah, right? GoFundMe or something. Yeah, you can see here, there's flip-flops everywhere in this chip. But you can see this is the overall of the device on Metal 1. And you can see this is where I got to. Why was I here? I was here because of here. This was the ROM output. There's something wrong with this picture when I did the cropping. You can see the edge of it still, but it turns white for some reason right there. It's something with the Photoshop version or something.
What kind of relationship do you have with Samsung's legal department?
I don't talk to them. No.
I mean, have they ever? I mean, are there legal protections that?
Nothing I'm doing is wrong. There's nothing illegal about what I'm doing. The lawsuit that I was in with News Corp, with NDS, for 10 years almost proved there's nothing wrong with reverse engineering an IC. It's what you do with the code you get out of it. For example, if it's pay TV satellite, which some of the people in here are familiar with, that's highly illegal because you're stealing, the right HBO signal basically, which it's something you have to pay for. To put this chip in the fib, the best thing to do is to throw it into acid and then glue them down into an 8-pin ceramic dip. These cost about $4 a piece, these little sockets. And then wire bond it, wire to here, wire to there. So this is glued down with super glue. So you'll see people in a fab using, special glues and stuff. But I want to be able to reuse the carrier later. on a different project. I throw them into a bin in like a glass jar, and I can reuse them later. I just throw them into acetone for 5-10 minutes, and then the chip falls off again because it was super glue. But you can see here's 2 chips prepped. I just didn't attach the wires yet. So next step would be to put them under the wire bonder and physically under the microscope connect the wires up: power, ground, clock, and data line, and the chip will, make sure the chip speaks, and then into the fib it goes. Thank you. I guess I'm out of time. Yeah.